This is the New York City AI Eng Meetup, and just some quick history about this meetup. I've been running it just on the side for the last year or so, for the last few months, and give credit where credit's due. Who here is familiar with Latent Space, the Discord community? Okay, a few people. So I started following the Latent Space, the Substack, and the Discord probably like about a year and a half ago. And Sean, also known as Swix, he runs the whole community. They also run various AI conferences around the world now. And I talked to him about, hey, I want to start hosting meetups in New York. And he was like, yeah, just go at it. And so the very first meetup in New York was like 20 people at Signalfire. They're a VC firm here in New York. And literally just 20 of us like sitting like in a circle kind of thing. And now we're like at Google, which is crazy. So this has definitely come a long way in the last year and a half. And yeah, I would say by far, this has been the biggest unlock for me in terms of letting my current role in AI is joining this community, going to meetups, talking to people. So hopefully this will be a good opportunity for you all to meet each other and maybe find your next opportunity, find your next customer, find your next partner. So big believer in bringing the community together. And if you haven't heard of Latent Space, would definitely recommend listening to their podcasts, joining their Discord server, and just being active in the community there, because that's how I started this whole thing maybe a year and a half ago. So big plug for them. And yeah, the way that today's going to work, we have a few speakers, two great speakers from Google, one from Modal, one from Galileo, my company. And we're just going to leave it, those presentations will happen. And then afterwards, the rest is just for you all to meet each other and network and meet and have a good time. Any questions so far? All right, so let's go into the first presentation. It is from Lukas from Google, and I'll have him introduce himself and explain what he's working on. I'll give it for Lukas. Don't mind putting this.
Oh yeah, sure. I get mic'd up. Arrange my things here. Cool. All right. Mic check. Yes. Amazing. Yeah. So first, thank you, Kashaf and Alan, for organizing this meeting. Not always the easiest thing to do, and also thank you everyone who's taken kind of a part in organizing this. I am a AIML customer engineer at Google. I have my computer science degree from Columbia University. I think I see a Columbia University sweatshirt over here. Yeah, shout out. And I've been at Google for about 4 years now. My start to my Google career was actually working on our PaLM models. Anyone remember the PaLM models? Yeah, couples, show of hands. 1, 2, 3, 4. Okay. This was Google's first answer to OpenAI back in 2023. And I was working with a bunch of our customers to get them into production status, and I actually worked with one of the first customers to bring them into production. But let's just say it was a little bit challenging. We're in a very different place now with our Gemini models. And in those 4 years, I've also seen the industry shift from more just like LLM focus, where you have basic chatbots, to more retrieval augmented generation, systems, adding in context so that you can have the right context for these chatbots. And then the next iteration of that being agents, where you can orchestrate multiple different components and multiple different of these systems working together in order to accomplish a certain goal. And now we're in the more complex agentic systems where we have long-running agents. Maybe they work asynchronously. Maybe we have multi-tiered agentic structures. And over the past year or so, I worked with a lot of our customers in order to bring some of these agentic systems, more complex agentic systems, into production. And so I have 2 key messages for you guys today. And there we go. The first key message is I want GCP to be the platform of choice when you think about building AI agents. I'll get into why. And then number 2 is I want Gemini to be the model of choice when you're trying to optimize across quality and cost. So I'll get into why. And the first slide that I kind of want to start talking about is Google Cloud's full stack approach. right? The full stack approach allows us to be the most performant and the most cost effective, whether it be on the AI infrastructure layer. We're the only hyperscaler out there that builds their own AI infrastructure. There are others now that are getting into that space as well, but we have quite a few years of experience ahead of them. We're the only hyperscaler that has an in-house model foundation lab, DeepMind, and that the combination of those two things eventually just lead to more performant systems, better engineering cost efficiency, and just cost efficiency in general. And I want to talk a little bit about, focus a little bit about the model as well. We recently came out with our Gemini 3.1 Pro models. Now, we built this model specifically to excel at agentic tasks. And you'll see that come out in even the types of benchmarks that we picked for this, right? We picked like SWE bench, terminal bench, and a bunch of others that were made for long-running agentic tasks. Now, the savvy folks amongst you will point out that this slide is actually outdated now. Both OpenAI and Anthropic, I believe, have launched new generation of models that might even come close to or exceed some of these benchmarks. But that gets me to my second point, which is when you are looking to build AI agents at scale, you need to optimize across not just quality. If you're building an AI agent that is for 10 users, sure, you can only focus on quality, only focus on latency. And it's very important. It's a very important benchmark. But when you're distributing this and going to production with this AI agent now for millions of users, cost suddenly becomes a big factor, right? And so when we actually compare some of these models on these two, I guess, benchmarks, for lack of a better word, and we graph them from price per million tokens on the x-axis and LLM Arena scores on the y-axis, we can see that the Gemini models fall along this Pareto frontier. The Pareto frontier is just a fancy word for an optimization between multiple vectors or multiple variables. And the two variables in this case are quality and cost. And so this kind of lands the message of number two. If you're looking to optimize across both of these metrics, quality and cost, select the Gemini models. To focus a little bit on our AI platform, we have, in the last year or year and a half, the amount of releases that I have seen come from this engineering team is not compared to anything I've seen before. And that resulted in a lot more adoption and a lot more developers actually trying out this platform. We see about 9 million developers building with Gemini and 20x increase in Vertex AI usage over the past year or so. And these are even outdated. These come from our second quarter earnings report from last year, 2025. So this has actually even increased over to now. And this slide is a little bit of an eyesore, and it is my last slide because I now only have 10 minutes. But we see a lot of these releases in this slide, right? So everything from our agent portfolio on the far left-hand side with ADK, Agent Engine, and Agent Garden. Agent Engine is a runtime for agents. Agent Garden is a place where you can go to discover and get started quickly with agents. This gives you all the tools necessary in order to launch your agents from a local environment to a more production-ready environment. And it's built on top of all this govern and orchestrate at the bottom here, where you can have telemetry, so you can go step by step in order to see exactly the actions that your agent took, what the tool call responded with, what the request was, and more. A quick note on that is each of these boxes, even the boxes within the boxes, can actually be taken as modular components. So we don't really care what tool you necessarily use. For example, we love ADK, we love Agent Development Kit, but we don't care what framework you use. If you use LangGraph, LangChain, True AI, custom framework, we don't care. Agent Engine will work with everything. Our models will work with everything. So we don't really care on that piece. The other thing that I'll point out is if you don't want to go with Gemini, you want to go with Anthropic models or Llama models or some of the other open source models out there. We have a model garden of over 150, I think it's maybe even over 200 models now that you can use and deploy within the model garden. And we know that not every model works for a use case out of the box, which is why we take in the platform and the custom as deploy section of the slide here, where we allow for prompt fine-tuning, we allow for model fine-tuning, and we have an evaluation service that makes it easier for you to evaluate your models for that specific use case, and various other methods. The thing that I am most excited for is actually this bottom piece here, because I think this is where agents typically fail in production. And what I'm most excited for, and I think you'll hear a lot of noise from us in the upcoming months, is the registry piece. I can't go into it too much, but the ability, a big challenge that we see developers facing in this space is just being able to track the telemetry, not just of agents, but also of your tool calls, whether they be Google Cloud built or third-party built, and be able to govern that across your organization, whether you be 100 people or 30,000 people. So that's going to be it for me. Again, the key takeaways that I wanted to deliver today are: number one, GCP should be your AI platform of choice for building agents. And number two, if you're looking to optimize across cost and quality, choose Gemini. Thank you. And over to Chris, I believe. Yeah.
I'm going to do a quick swap. That's all right with everyone. Let's see how we can do a quick adjustment on the tech. All right, I have 5 to 10 minutes. Let's see if I can run through some slides and show a quick demo, if everyone's okay with that. Cool. All right, welcome. Thanks for coming to Google Cloud. Glad everyone made the time for tonight. My name is Chris Page, so I am in Google Cloud's AI engineering organization as a Gen AI black belt. No, I do not use my arms to chop tables. Yes, I do solve technical challenges for very high-profile customers and work with the brightest in Google DeepMind and Google's engineering organizations. My team is responsible for all of the Vertex portfolio of products that Lukas was showing you in that big slide, as well as bringing all the Gemini models onto the Vertex AI platform. And what I do is I basically use my background and technical depth in software engineering and system architecture for the last 20 years to help unblock challenges through those enterprise customers to accelerate their adoption of Gemini and Google Cloud products. That can range from simple prompt engineering, prompt optimization, contextual engineering, all the way to supervised fine-tuning, low-rank optimization, and many other things deeper in the stack. But I've been a little bit about myself. I've been Google Cloud for this role about 1.5 years. Before that, I was Capital One for a little bit, and I was also in Google Cloud before that. But I've been basically in software engineering for the last 20 years. Started out racking and stacking cables for the government. I really liked getting my hands dirty and learning about the technology, but realized software is the next thing. And then made my way from building open source applications, leading software development teams, to actually then going into big data modernization, more predictive and regression-based machine learning, and then ultimately to large language models, which you guys all know today. Everyone knows there's a shift happening. I don't have to repeat 2023, more textual-based models that were coming out, GPT, BARD. We're actually seeing a lot more shift now to the multimodality. Text isn't the only interface that large language models are encoding and decoding and providing those summarization or contextual responses. We are seeing a lot more autonomy with agentic approaches, with more decisioning. more reasoning capabilities and providing those applications the ability so that they can make those decisions without human intervention. There are various different verticals and industries where that's not completely possible, like highly regulated industries like healthcare and financial services. You'll still have more human in the loop, but there are various different tools and mechanisms to make sure that models perform how you want them to perform. And I'm not sure if everyone knows this, but Gemini 3.1 is our flagship foundational model. We just released a new preview version just recently, handling up to 1 million tokens. But the biggest thing here is the ability for multi-turn interactions using a mixture of experts architecture, being able to give the user the ability to provide configuration-based approach, determine how the model is going to reason, whether it be more probabilistic to understand contextually what is the user trying to determine and make decisions about what tools or what functions it should use, or more deterministic and forcing it to go back to the client to make those more low-level or POSIX types of decisions that you would typically do in computer science, i.e. if you need to do any unit tests, compiling tests of your software engineering, you see a lot more coding agents using local CLI-based tools. With Gemini 3.1 Pro, we have both speech to text-to-speech, image encoding, encoding, decoding, as well as various different tweaks within the thinking mode to give you the flexibility and the ability and the power to make sure that you can utilize the models to the best of your use cases. I'm going to get a little bit more into details about the video and audio aspects, but for now, I think Lukas talked a little about kind of the more cost-effective option with Gemini 3.1 Flash. So still having the power and capability of multimodal processing, but also giving the flexibility for more cost-effective and more real-time millisecond interactions for inference. We typically see use cases more on routing capabilities to determine more intent classification and contextual kind of understanding of query translation that then gets routed to other more intelligent models for more larger tasks like Gemini 3.0 Pro. It doesn't stop there. If anyone's familiar with Nano Banana, a little bit, some nods. Nano Banana 2, basically multiple text and image inputs, combining that capability. We just released Nano Banana 2, Flash 3.1 Flash image. Moving along that, there's that capability for those content creators to generate the various different images, but also alter the capability with not just textual, but also image-based inputs. VO, our flagship video-based model, allows the user to also not just put the textual base from text to video, but also now you can actually use image to video in high-def 1080p and 4K resolution with the extension to 15-second videos. Moving down the line, we also have our latest speech-to-text-to-speech models and Lyria to actually using the ability for multiple genres to create new music and content, and putting all that all together, we're seeing a lot new kind of complete end-to-end playground and pictures of full generative kind of video with all the different capabilities of the Google models. Now, what happens is we have all these different capabilities and all these different use cases. What if we want to put it all together to have real-time interactions and bidirectional communication with various different agents and generative AI apps? This is where Gemini Live API comes into the play. We had an early version earlier last year. It was still on the 2.0 model family. We're now moving to 2.5 and soon to be 3.0 Gemini in the background, but using the same mixture of experts, the ability to do encoding on multi-different audio and video and textual inputs, but also be able to give the user the ability to configure what different types of interruptions they want to configure for the model to break that interaction, what different types of persona that they want the model to respond with, and various different interaction and reasoning capabilities similar to the thinking ability that is in Gemini 3.1 Pro. In a traditional kind of pipeline, we would see customers orchestrate the various different models from client all the way from input from speech to text to encode the audio to textual, do the reasoning and classification with a traditional, basically a foundational model, and then actually go back to text-to-speech and decode back out to the client. That introduced a lot of, the experience was it wasn't poor per se, but it wasn't in real time. So with Live API, we're actually introducing all those decoding capabilities for all the various different modalities, all within the model architecture itself, and serving it over real-time WebSocket API interfaces. Traditionally, we have all of our Google Cloud services through API and gRPC, but within a bidirectional communication so that the client and server are sending information and packets back and forth in the same time in a multiplex or dualplex operation, WebSockets was the choice for this. I have a simple architecture. If anyone's familiar with kind of 3-tier architecture, typically in a single page app, you have a client on the left, the application. You have basically a proxy or a web server, a WebSocket server, which handles all of the authentication, the session initiation, and the communication to the WebSocket endpoint for Gemini. This would be a similar type of generative AI application you would do just for a traditional like Gemini 3.1 Pro or Flash. But in this instance, we're going to use a WebSocket server so it can actually persist those connections and handle the communication back and forth from the client in real time. Let's see if I can do a demo. All right. Can everyone still see my screen? All right. I am dating myself, but I'm going old school in Vim. Emacs or Vim users? Do I have anyone here, or is it all IDE? Vim. All right, cool. Simple app. This is all available. I'll share the links. Basically, wrapping WebSockets, instantiating the communication, creating the proxy, starting the server. I won't go into full details on that, but let me just make sure that's working. And then just a Node.js or JavaScript app. Give me a second. I'll show you real time. All right. Can everyone see my little SPA right here? All right. I talked about the initial configuration setup that's required within that server for Gemini Live API. Basically, it's your WebSocket URL, project ID, typical generation config with system instructions and the various different model tweaking parameters for like temperature. But in addition, you can choose the type of voice that you want. You can use first-party tools like Google Grounding. You can actually add additional transcription capabilities. And then you can set more configuration on how you want it to be interrupted if there's any background noise through the audio transcription or the audio streaming capabilities. So if I just connect, you'll see that should be going through. And then I'll just, for now, what can you do?
I can help you with all sorts of gaming stuff. Got a question about a game, need help with a strategy, or just looking for recommendations? Let me know.
All right, let's see. Let's change the persona and see what else we got going on here. Hold on.
I can commune with knowledge, generating text, translating languages, summarizing wisdom, and even crafting verses, traveler. What truth do you seek this day?
Yes, that's great, Wise Wizard. I'm not setting up my audio to talk to you right now, but let me just share my screen. Actually, hold on. I'm not a gamer anymore, but I have a nice little GIF to see if we can. Does anyone know what this? Oops. Let me go back to it. Does anyone know what this little GIF is from this game? No? All right, good. Neither do I. All right. Let me share my screen and then go back. All right, so I'm sharing my screen. Or how about, where am I?
You have found yourself within the Cinnabar Sands, traveler. That towering machine you see, the tall neck, paces about here. Are you intending to climb it?
Before I make any harsh judgments on what I want to do, I just want to show you the output there. You'll see the multi-turn capabilities that I mentioned before, basically request response, and then a summarization of the different types of inputs with textual, audio, and I think video chunks I'm capturing. Yes. Okay, great. Let's see what else we can do. Can you help me get out of here?
To leave this region, traveler, you must first climb the Great Tall Neck. Seek the nearby satellite dish. Restoring its power will create a path. Do you wish to proceed thus?
And you get the idea. But basically, this is a real live in-game assistant that can help me cheat because I have no idea how to do this game. But we see similar use cases for like wealth management or customer service. So all different verticals, but this is just one example that I think was pretty cool. All right, let's see what else. Just to basically summarize, Gemini Live API, it's serviced on both AI Studio, but Vertex AI with our enterprise capabilities of scalability, high performance, security, governance that you would expect when you're building out more robust applications. I'm not going to go into all the details of all the different capabilities, but I will give you the links if you want to try out any of those apps and some of the blog content for Live API. See if any of those QR codes work and they don't get messed up. But that's it from me. Any questions? Or do we have time for questions till after?
One or two questions.
Okay.
Any burning questions?
Got my first workload ever deployed to GCP, and one of the big challenges is like it's just me, and I have to always figure out what to enable inside of GCP. So I have a workload right now, and I have Google Cloud Run set up. I have some services set up. If I wanted to add this in, like how many steps does it take?
That's a great question. I'm not sure if everyone else heard it, but what are all the dependent services in Google Cloud to enable Live API? There actually is only, I believe, 2. And in that developer blog, you should see where it would actually prompt you for the enablement of that particular services. It should just be IAM and AI platform to enable that. But don't hold me to that because I already had it enabled, but it should be self-service in that capability.
You have, because this is collecting UGC, do you have any restrictions on like how it can be, like, let's say, used, or age restrictions or guardrails?
So inherently, out of all of the Vertex AI platform and Gemini, we have safeguards in place for sensitive information like child or pornography, and that there are different guardrails that you can remove, but it requires basically a more, I think Lukas might know directly, but it requires kind of working with the account team or working with your support team to have justification for that. There are some monitoring that we won't remove at all, just because for privacy and safety reasons. But there's also additional customizable guardrails that you can implement as well if you need to enable them for your application when deploying it.
Thank you.
Go. Sure.
So my question is with how sophisticated this multi-agentic systems are getting, what traditional systems like search and recommendation, as important or less important, less relevant?
So the question is, as multi-agents become more intelligent and more prevalent, what about traditional systems? Would they be more important or less important? As you see any technology shift, it's kind of providing more information or more capabilities to make it more seamless or personable or customizable for the end user. Whether that end user be someone in a large enterprise, like B2B, whether it be an employee. What we're seeing is a similar shift in being able to surface and make those information more customizable and personable for particular users based off the context that you enable or you provide for that capability. So let's say search itself, it's traditional, let's say a Lucene search index, which is more keyword based. Now we introduce more natural language with adding synonyms or adding your additional kind of preferences and capabilities so that we can surface that information that's more catered to what you're looking for. So I see it as multi-agents kind of shift, there's still a different capabilities and features that you would enable to provide more customizable or personable kind of results for you.
Regarding the station, assuming when you use multimodal, your context in a window usually gets full easily, right? If you use audio or a start screen share, so how you can prolong that session, strategies are there.
So typically there's a model-based KV cache. We also have a persistent kind of session-based cache that the model can use, similar to a RAG-based approach. And also there's client-based cached, whether that be in like the proxy server or the actual SPA app. So there are limits on the model cache. And what happens is what we'll do is there's a certain cutoff point where we'll then have it go out to a more persistent cache. And that's configurable based off of how you want to deploy and make that architecture.
But in production, how you make sure that it does not end on the session itself model and how it basically gives the user seamless experience.
So typically, similar to like cookie session IDs, you have session management or session IDs for each one of those different streams. With those streams, you're able to monitor with validation on whether or not those sessions would hit a particular limit. The model itself and the API will also provide basically almost like if you think of an HTTP 400 like bad request, it will actually give back that response where on the client, then you have to be able to interpret whether or not starting a new session or repeating an existing session. So some of it's handled in the actual backend infrastructure. We provide some of the metrics on, but also basically session ID and managed through the server as well when you're building the application.
Right. Thanks so much, Chris.
Sure.
Thank you. All right, next up we have Jason from Modal.
Hello? Can you guys hear me? Cool. Sweet. Thank you. Okay, hi. Who here has heard of Modal before? Oh, wow. Awesome. Cool. Okay, pulse check actually. Who here has run AI code in Sandbox recently? Maybe indirectly or otherwise. Okay. And who here has run code on a GPU recently? Cool. Okay. Sorry, just trying to like calibrate because this talk was like it was given at NeurIPS this year, and it's look behind the curtain at how we do things at Modal internally. But so for people who haven't heard of Modal, there are a few of you. So the thing that we do really is we give you access to compute very quickly in a Python SDK that just basically takes a Python decorator or Python function, wrap it in a decorator, run it in the cloud. Very easy. Or probably the easiest way to get GPUs, just like generically, you sign up, you spin up, you write a function, say, I want an H100 for this function, and you run it, and it basically just works. And yeah, the other reason you may have heard of us is because a lot of people use our sandboxes to build various like agentic coding style apps, like the vibe coding platforms use us. Some people use us for agent evals for their agentic systems. They like when they execute code and they want to basically sandbox that execution. Then other people use us for RL rollouts. So if they're actually doing reinforcement learning and fine-tuning models, usually open source models, they'll use our sandboxes to essentially execute the agent's tool calls during training. And so yeah, that's sandboxes, but we also have a lot of GPU capacity. That's like primarily why people come to us. And we're like a serverless platform for using all this kind of compute pretty easily. So yeah, the agenda here is basically to build us up to understanding kind of the scope of the problem that we're solving here. The idea is, okay, recycling the world computer. If you think of Modal Modal, what we do is we aggregate demand across customers. We go to the hyperscalers or other cloud providers. We take that aggregated demand and say, hey, we have a lot of demand to run compute on you guys. Will you give us high quotas? And they always, for the most part, say yes. And then that gives us a plan or a problem then of basically saying, we have all this customer compute to run. We have all this cloud capacity to run it on. But there's essentially like this arbitrage problem that we have to solve, which is knowing that our workload is this big and knowing that we get capacity from all these different cloud providers over here, which ones do we actually decide to spin up compute on and run those customer workloads? And basically what we do is, I'll get into it, but we solve this problem every day, actually every 5 minutes, and we basically automatically move our fleet around to account for how much customer demand we have, but also what the current prices that we can get from cloud providers are. And so what is Modal? It's basically just, that's our system. And I'll give like a quick crash course on how we do that, and then talk about basically what kind of problems this leads us to consider, and then how we're thinking about fixing some of those problems, mainly around idle compute and the buffer capacity that we want to provide, but don't want to waste. So unfortunately, this was like a, yeah. Oh, did you request it? Maybe I can check. It's important, so let me see if I can. Cool. Oops. Okay, we got it. Nice. Oop. Does that work? Cool. Okay. So what this video shows is me running a Modal app. It's just a quick demo. Basically shows me taking this function run on GPU and scaling it up in the cloud. Basically, I don't care what GPU, I give it like a list of all these GPUs, and then I print out some information about where the code is actually running. You'll notice that this is in a bunch of different cloud providers. So we have GCP, OCI, Azure, AWS. We also have different regions. So some of them are happening in Europe, some of them are in the US West, US East, Central. But essentially, yeah, when you just have a function to execute on a GPU, and you don't really care about all the rest of the infrastructure side, you write this function in Python, wrap it in a Modal decorator, say I want these kinds of GPUs, and then just run it. And as you can see, in about 30 seconds to a minute or whatever it's been, we got up to about 112 containers. So this is 112 GPUs in the cloud, just based on a single map over 10,000 inputs. And so the question is like, how do we do that? How can we offer that to our customers? Because I think usually it's quite a bit harder. Maybe you can get like one node of 8 GPUs, or maybe you can get like a cluster of some amount, but then usually you have to go and get a reservation. You have to do all this stuff to enable, even just have the ability to pay someone to get that compute, let alone you have to then configure your own EC2 instance or your own Kubernetes cluster or all these things that kind of we try to handle for you and abstract away from you. Because at the end of the day, I think most of us in this room are just writing our code and wanting to run it somewhere, and we don't really care too much about the details of how that happens. Okay, so I won't go too much into the user experience anymore. I'll just talk about, like, from a platform perspective, how we do this. In that demo, it happened really quick, so maybe we didn't catch it, but what you would see if we watched it back was that how many containers we got, aka how many GPUs we got, was variable over time. So the first thing is that, like, we have a large buffer of compute that we just let sit around and let be idle so that customers can scale up really quickly. So that's what this like first initial bump is. In the early moments of running that function, you should see essentially like a quick burst of us just giving you as many containers as you requested. After a certain point, what you'll notice, if we let that run out many more minutes, you'd have seen this like plateau of like slower GPU acquisition for the function. What that essentially says is that like you've burst up, you've exhausted the buffer of idle capacity that we had. So now we're like going out and getting new nodes for you. But this takes time because the cloud providers all have very different kind of speeds at which you can provision compute on them. Actually, GCP is one of the fastest. But yeah, essentially what this means is that our goal for this is that you should be able to run a function, burst up really quickly, and over time, essentially have unlimited amount of compute that you can get through our platform, ideally. And we have people running thousands of GPUs for a single function. This does scale out quite a bit. So yeah, what's our secret? There's a few things we do that enable this beyond just the capacity story. We rebuilt our container runtime so that you could have near instant cold starts. The main thing is that this is based on like lazy loaded content addressed images. Let's say you're running Docker. The problem with Docker is that you have to download the entire image, unzip it, unpack it, and then basically say, okay, here's the file system I'm going to run in. I'm going to start running it. But that's wasteful, especially for very large images. You shouldn't need to download the entire image when your function is only going to use maybe 10% of the files in the image. So what we did was we rebuilt the container runtime in the image format so that we could fetch files individually and start running as soon as the files we needed were available. Yeah, we have a whole talk about this, so I won't go too much in depth about it. But the second thing we have is this large elastic global compute pool. It's multi-cloud. It scales dynamically in response to our user workload demand. So that's why we can basically say, okay, once you scale up really quickly and burn through our buffer that we have, we can continue to allocate more and more compute for your function as long as you're requesting more of it. Yeah, so we have this multi-cloud substrate that we run this on. I think when I wrote this talk, we had 5 total providers. I think now we have like close to 10, maybe more. So we're always adding more. And yeah, as I mentioned before, we have this, not just the logistics problem of workloads that we need to run and like, how do we run them or where do we run them? It's also an arbitrage opportunity in the sense that we get certain prices from different compute sources, and we can essentially try to run this as cheaply as possible given the constraints that our users provide us. So for example, if one user wants to run in US East 1 Amazon, then we can't really do anything about that, right? But if someone just says, I don't care, just give me 1,000 GPUs, I want to run all this batch stuff on, we can be very choosy about where we run that compute based on the cost of running it for us. Yeah, so here's actually how we like implement this. We implement it as a linear program, which is essentially a fancy way of saying I have this big many variable optimization problem that I want to solve. We add in the different parts of our system that are dynamic as inputs. We also include like the constraints that we care about. So some of the constraints that you might see here is we have this 8xi greater than a plus b. That's basically making sure that we have enough instances with 8 GPUs each in order to run the user workload plus some buffer. And then this other constraint, which is xi less than li. This is basically in each cloud for each worker type, we have some quota. But actually, we've gotten large enough quotas from most of these providers that they actually don't satisfy the quota to us. We'll observe scaling limits before we even reach the quota, where they just won't give us any more instances from this cloud in this region of this worker type. So we actually feed those observed limits back into this problem so that the next time you solve this problem, it'll solve with respect to those limits that we've stumbled on by trying to start instances there. So this basically means that like as long as you're solving this linear program consistently, our fleet will eventually adapt to fit the shape of the compute that the cloud providers give us, and eventually we will, guarantee to scale up to as much GPUs as we need to solve this, essentially to run this workload. This is what that looks like as like an architecture diagram. Yeah, as I mentioned, we like scrape the prices, plug those prices plus our user workloads into our solver that spits out this linear programming solution. And then we take that solution and just start spinning up instances everywhere that the solution has dictated us that we do that. Any questions before I move on real quick? Yeah. What I presented is actually a simplification, and we do account for that. So we have a timeout parameter, which basically determines the upper bound of execution that is user specified, and then we use that timeout as like a worst case, and then plan around that. But then if it exits early, then the scheduler will essentially notice that and like essentially schedule a new user task in its place as soon as the execution is done. So this is handled more efficiently, but yeah. Yes. No, not currently. Yeah. We have 0 priority, so it's first come, first serve. Yeah. But maybe one more, and then I'll. Yeah. Yes. Yeah. So we basically give you. I don't actually know if I have any. I don't think I have any code except for the earlier demo, but there's a cloud parameter and a region parameter. If you want to constrain the scheduling of your tasks, you can do that. We also have other constraints like we have a new multi-node training product where we basically need to gang schedule multiple containers in one particular cloud and region so that they can communicate efficiently to each other. And that's one where it's like it's a much heavier constraint than is normal. But sorry, I want to like get through some of the stuff so we can take questions at the end again. Cool. So there are a few different sources of idle compute in this picture. The first is that we have the number of GPUs we need. So I'm simplifying a little bit. We do CPU as well. So we split up CPUs into the number of cores and the amount of memory, and we partition our workers that way. But we also, this talk is mainly about GPU computes because that's like the largest source of cost, but also what most people know us for. And yeah, this buffer is essentially how many GPUs are free in the fleet. So if we're running, let's say, 1,000 instances and each of them have 8 GPUs, then we have 8,000 total GPUs. If our current customer workload only requires 6,000 GPUs, And then there's 2,000 GPUs somewhere in the fleet available. This is just buffer capacity. And we provision this specifically so that our users can burst up like on a moment's notice, right? You don't want to wait on us to provision new compute to be able to burst, especially if your app, like someone comes along and starts using your app, you start going viral. You don't want the app to just like choke on all of that traffic, right? That is what we have the buffer for. So that's one source of idle compute where it's just by definition, by virtue of what we're trying to do as a product, we have to have idle compute in the fleet. Now it is fragmented. Those 2,000 GPUs might be scattered all across the 1,000 workers in the fleet. You might have 100 workers with no free GPUs. You might have 200 workers with one free GPU, and then you might have a handful of, or all the rest with like somewhere between 2 and 6 GPUs available or that kind of thing. Or you might even have some workers that are completely empty. So that's one thing. As I said, that's intentional. This is like over provisioning so that we can burst up pretty quickly. There's also this concept of draining workers. So because we're constantly running this linear program to figure out where we can run our compute the cheapest, there are workers that we've said, okay, we no longer want this worker because it's too expensive, but there's existing user workloads running on it. And we don't preempt our user workloads at all. Like we wait for them to be finished. So when we basically have marked a worker and said, okay, we're going to kill this and get it off the fleet, we have to wait for user workloads. And if someone's running like a training job on that, for example, that could take up to 24 hours for them to be done. We have a hard limit as 24-hour timeout on all functions, which we give you tools to like retry if you're doing multi-day training, but the idea is that like those workers need to be, called quickly. So this is like an area where we have a lot of idle capacity just because we've decided it's too expensive to continue running this worker. Okay, so now that we've talked about these two sources of idle capacity, I want to talk about this concept of recycled compute, which is the idea of what if we could take that idle capacity and reuse it. Essentially, it's just whenever we have an idle GPU, whether it's because it's part of our buffer or because of it's part of a draining worker, we can just run user workloads as long as we don't make guarantees about the execution of those workloads. So as opposed to what I said before, where if you have a function and it's running for however long, let's say 24 hours, we basically will run that for 24 hours unless the cloud provider preempts us. We'll never preempt your function. The idea of recycled compute is that we might give ourselves or our customers a tier where you opt into this and say, I'm going to run this batch job, for example, on this idle capacity for a discount. And then we will essentially kill your function execution when we need the GPU, whether it's because someone else bursted up or whether it's because we've decided that like running this worker is too expensive anymore and we want to cancel it. So yeah, that's the idea of recycled compute. It's can we take these two sources of idle GPUs and reuse them? And for this to work, we need to be able to like essentially sig kill it and do that in milliseconds because we want to be able to take this idle capacity and schedule into it immediately, like in milliseconds, right? But if we can do that, then we can potentially use this recycled capacity for stuff. And the first question is, okay, how much recycled compute is actually available? And the answer is it's quite a lot. Now it depends on which GPU types you include. This top row, around 100K GPU hours a month, is just for H200s and B200s, which are above 140 gigabytes of VRAM. If you admit 80 gigabytes of VRAM or above, then that increases to 300K GPUs hours per month. And all the way at the bottom, we have this, if you just don't have any VRAM requirements, then 1.2 million GPU hours a month. This is a lot. For context, DeepSeek V3, pre-training and post-training altogether took 2.8 million GPU hours. So we're basically, okay, there's a lot of like hand waviness here, but basically in 2 months or 3 months of all across our entire fleet, we could train a DeepSeek V3. Okay, not really, because there's like a lot of caveats and they were running like a single cluster and this is all fragmented, but point being like there's a lot of compute here. Okay, so the idea is like if we had this recycled compute primitive, what would it look like for a user's function? Whereas this was the original one, which is like our current modal functions, you're always guaranteed to gain capacity and pretty much never lose it. For a recycled function, it would look like this, where maybe you initially burst up and get a bunch of GPUs, but as time goes on, those GPUs just get really quickly preempted. So you actually might have like negative growth in the amount of GPUs that you have because you're just going to be like losing and gaining and losing and gaining GPUs in your function, in your container pool. So yeah, this is a totally different shape of compute, I guess you could call it. It's massively parallel, which I think is like similar to the rest of our fleet. It has this like heterogeneous hardware. It's highly available in aggregate, but it's low availability for any one device. So this basically means like any one device is like highly likely to be preempted, but overall there's like a lot of compute here just sitting out there able to run stuff. And then the last is that the interconnect is like basically you have to plan for the lowest common denominator, which is basically over the internet. You don't have like high data center interconnect like you would normally. Also, the containers could be in like completely different regions in completely different parts of the world. So if we want to run tasks on this recycled compute, what is like the best sort of task? It is massively parallel. Ideally, it's hardware agnostic. It's re-entrant, which means you can checkpoint it and resume it easily if it gets interrupted. It's parallelized fault tolerant, which means that you can make progress as long as the entire thing keeps going. You can preempt individual tasks or containers, but still keep making progress. And ideally, there's like little to no communication between these containers. So I have this like graph of all the kind of like machine learning type tasks that you might want to run. So there's a couple classical examples like protein folding or molecular physics simulation, which are accidentally very good for this shape of compute. You have, let's say, moving into the more modern stuff like the LLMs, you have offline batch inference can be shaped pretty well for this. Synthetic data generation can also be shaped pretty well for this. And I put this one last, distributed LLM training, because it's like, it's the worst. It is generally not fault tolerant. It has a ton of communication, and it's not hardware agnostic. So it turns out that like people have been doing machine learning training in this regime for quite a long time. Actually, the people at Google have. And it's called federated learning. In the land of LLMs, it's called distributed low communication training. There's this DeLoco optimizer, which is built for this purpose of training a single model across data centers. And there's a bunch of like really cool work following up on that original work, showing that you can actually scale pretty well. And as you scale, the benefits of doing training this way actually grow and grow. It's like a nice scaling law for it. So that basically says, okay, we can do training in this like low communication regime, but could you do it with fault tolerance? And the people at Meta actually showed that, yeah, you can, which is this idea of fault tolerant LLM training. They trained a llama model, I think, with an extreme amount of failures, with 2,000 failures every 15 seconds, with no checkpointing. Basically means they were able to like, as long as the entire fleet stayed up, no matter how many individual GPUs they killed, they kept making progress on the whole training run. And this is like the loss curve from that blog post, which is pretty cool. And they even open sourced their code. I wouldn't try this at home. We tried it. There's a lot of issues, tons of egress. So yeah, I think like what we've found is that the best use case for this kind of compute is like batch inference or evolutionary algorithms are actually really good because you can bake redundancy into the algorithm, which allows you to make very good progress the entire time. Thanks, sorry. I know I probably ran over, but yeah, we're hiring and can talk to you about Modal if you're interested in what we do. Thanks.
I assume you'll stay after if we want to talk to him about creating Modal. So thanks again, Jason. All right, we're running a little behind. Last but not least, we have Sudhir from Galileo. He flew in all the way from California. So thank you, Sudhir.
All the way from California.
Yeah.
The best state ever. You know? Cool. You know what's one big, can y'all hear me? Yes? All right. San Francisco versus New York, yeah? I was saying, what's the one big difference between the two cities? Okay. San Francisco, no matter where you go, if you all been there, I'm sure you have, AI billboard, AI, everything is AI, right? As I was traveling in New York City, so I landed this morning, and I took my Uber, came to the hotel. I counted the number. I'm not seeing any AI billboards here. Nothing's happening. No, I'm just kidding. What I did see was a lot of psychic. And I was like, man, I want to do that. I want to get into one of those psychic, whatever they are, and ask for my fortune. So anyway, instead of asking psychics, what do you all think about the AI thing going on right now? Is it going to succeed? Is it a hype? Is it just not going to succeed? Depends on who you ask. Definitely do not ask a psychic. But if you check with MIT, Gartner, Deloitte, etc., this is which is, there seems to be a groundswell of folks wanting to go take their interesting apps to production, right? We just saw Gemini. It's come such a long way. It's super awesome. I played around with Nano Banana, of course. Haven't yet played with Gemini at the voice thing, but I will surely do that. But anyway, this is what the state of the art says. Now, if you look at the positive side of it, there's at least 93% of the leaders claim that they want to take their AI agents to production within the next 12 months. And there's a $15 trillion TAM to be had in this area. So that's what the optimists are going to say. The pessimists, what are they saying? They're saying, what, of the 100% of enterprises that are going to launch AI agents, 23 of them already have a formal pilot going, right? But only 5% of them, 5% of them are actually going to reach production. And out of that, only 2% are actually going to deploy it at full scale, as in 100% of their customers or workflows. Most will sadly fail, right? That's a bitter truth. But why would they fail? And this is an important slide. They failed mostly because of reliability features or reliability failures, which happens when you have no visibility, as in you do not know what's going on. The architecture diagram looks beautiful, it's all great, but then there's so many failure points, and you do want to know where it's failing. Did y'all get the t-shirts over there? Did you see there's a gremlin in there? On the t-shirts? What does a gremlin mean? Anyone? What does a gremlin stand for? Mischief, that's right. It's a World War II reference, by the way. And gremlins are hidden creatures, and you do not know why your aircraft failed or what happened in your machinery. So it took off from there. So that's the case with AIs too, which is it works fine when it does, and when it does not, you do not know why it failed. So observability is very important in the world of AI. Now, when it comes to AI, there's levels of maturity. How many of you here, if you don't mind, tell me, have got multiple agents, multi-agent architecture deployed in production? 2, 3. Wow, what are we going to do with all this infrastructure? Jason, man, what do we do? Anyway, hundreds of GPUs being spun for 3 folks in the room that want to build multi-agent applications. Now, I bet there's more. I hope there's more. But anyway, as you build these applications, what you'll notice is that there's levels of maturity that you will need in order to have the comfort, the confidence that you can indeed deploy multi-agentic architecture to production, right? We do have, over the last 3 years now, the things on your left-hand side, there's a lot of orchestration frameworks, SDKs, CI/CD tools, a lot of that. What we really do need is a way to observe these agents and to tame them. Let's see. Let's build. And Galileo, that's what we are. And Galileo has the observability platform. You saw earlier slide from Google. They are super happy if you want to plug and play. So for the eval block, plug and play Galileo. And so let's do one thing. Since we are in New York, is known as the financial capital of the world. So of course, we're going to come up with a demo app that's going to be about stocks. All right. And then let's see how we're going to use Galileo. So to set up this foundation for that app, yeah, we will build it as a multi-agent application or architecture. We will hook it up with Galileo for observability. We will observe what's going on, as in we'll understand the issues, toolchain errors, etc. And finally, this is the fun thing. It's called agent control, which I'll keep for last. All right? All right. Anyone familiar with the Gang of 4 patterns? Software pattern? Come on. End of the day, right? All right. So similar to Gang of 4 patterns back in the days, now there's an emerging architectural pattern for multi-agents. As you can see, peer-to-peer communication, orchestrator pattern, etc. So for the demo, we're going to choose one. We're going to integrate it with Galileo. And it's going to be super simple. Doesn't matter which particular orchestration framework you use or LLM model you use, very little code is required to integrate with Galileo. Just a few lines. So once you do that, we have a demo going. What's the demo? We'll have a financial advisor agent who's going to employ 2 agents, one a bull agent, another one a bear agent. Of course, the bull agent is very optimistic, the bear agent not so much, and they're going to fight with each other. to come up with a score on whether you should buy, hold, or sell your stock. Of course, there's going to be a chat agent that you can converse with. Okay, all right, so I'm going to fly through these slides. These are the code things. So yeah, all you need is a few API keys, and here is the demo. All right, here is our financial agent, multi-agent architecture and application. So as you can see, there's a toolchain call, there's a financial advisor AI agent who employs a bull agent and a bear agent, and they're going to duke it out with each other. Let's look at the stock NVIDIA. Why not? Because it's an AI bellwether stock, right? So let's hit analyze, see what's going on. It's fetching the market data from Yahoo. And at the moment, NVIDIA is at 176, and a whole lot of other statistics that like P/E ratio that are important. And as you see, the debate is raging between the bull and the bear agent. The scores are lining up here, as you can see in the scorecard. The prompt suggests that they have to converge, and there they go. They are converging. It's taking a while. Round 3. There you go. Within 3 rounds, they have converged. And here's the verdict. The verdict is to hold. Each of the agents came up with a risk factor. They duked it out with each other. They came up with a hold. Here's the chat agent. Let's ask some questions. There you go. It's now summarizing the result. Now, you know what? Because they've integrated Galileo observability, we can see all of these activities in Galileo. All right, let's do that. Behind the scenes, I use those very simple 3 or 4 lines of code to integrate with Galileo. Yeah. And now we'll see all of these interactions. All right, now that we saw the demo, financial agents, here is Galileo, the observability platform. This is the free version that any of you could register and sign up for. I did for my application, and here's the financial analyst agent. It's got a couple of log streams. One was a demo one and one in production. So I had logged the production, and it was an NVIDIA stock, as you can remember. So here we go. Let's look at the NVIDIA one. If we look at the sessions, this was the last one that we did for NVIDIA, as you can see. This session has got a few metrics that I pre-populated for Galileo to compute: agent efficiency, agent flow, agent completion, conversation quality, etc. These are some of the metrics I selected earlier. However, there's a lot more out of the box of preset metrics that you could choose. And in fact, you could create your own LLM as a judge or a code powered metric as well. So once you do that, the fun thing is in looking at the actual traces. These are the traces for the invocation. You can look at the toolchain call, how long it's going to take, any of the metrics that you want to see if it works or not. So a whole lot of information. Here's a fun one that I like, which is the agent graph. Here, it shows a wonderful graph of the actual invocation. In fact, after we have a lot of traffic, it shows where the majority of the toolchain calls or traffic goes from one agent to the other. So yeah, a whole lot of observability data. Now, of course, more fun coming up. All right, let's go to agent control and see how we can prevent actions or bad actions from taking place and controlling your agents. Okay, so what we did thus far was we built a demo application, right? And then we hooked it up with Galileo to observe and evaluate and monitor what's going on. But that's passive. What if you want to prevent badness from happening? What if you want to prevent policies being disregarded? That's where our newest offering, Agent Control, comes in. And it's in fact open source. So let's look at what is Agent Control. With a simple command, you can install Agent Control yourself. In fact, you do not need Galileo. It's completely open source. You can host it yourself, or you can choose to use Galileo as a server. Let's do that demo. We are back. So remember, we were using our financial advisor agent, and one of them was a chat agent, and we asked it to summarize key points, etc., which it was able to do. Now, we're going to add agent control to the chat agent. In other words, I don't want certain critical information to be passing between the agent and the human. For example, block SSN or block PII input. So as if you can see this screen here, there are regular expressions that are created that allow us to block emails or SSN. Let's see if this holds. Okay. Send and to at gmail.com. Now let's see. Oh, there you go. Our agent control is in action, and it has now trapped that as a sensitive PII information. I could turn it off by saying, all right, you know what? It's fine. Go ahead and use those. Now, if I do the same thing, let's see, there you go. It passed through. However, the prompt for the chat agent said it should only focus on stocks and market, and hence it went to that action, which is an legitimate request. All right. That was that. So in other words, it's great if you want to build multi-agent, go with confidence, provided you have a great visibility tool that gives you the confidence, the observability, the eval engineering framework, and the ability to prevent bad things from happening. Towards that, we've got also a lot of resources on the Galileo website, ebooks that would give you the foundation to learn about how to build multi-agent complex applications. And of course, we've got agent control. It's not just about preventing. You can steer, you can audit, you can block, and without any code, by the way. In other words, all of these are just affected on the server side in terms of configuration. So you do not have to intersperse your code with a lot of logic on what should happen, should not happen, etc. It's a pretty interesting thing. I'm going to give a plug-in for a seminar or a webinar that is coming up on the 25th if you want to register for it. With that, thank you for joining us all. Great talks, and enjoy the rest of your evening. Al, take it away.
All right. Thank you, Sudhir. That ends all the talks. I think I had one slide left. No? Yeah, just one more plug for agent control. On the field engineering team at Galileo, it's something I'm using every day to help our customers out. So definitely something to check out. Lastly, just want to thank everyone at Google who's here, for Chris and Lukas. Give everyone a big hand at Google. We're big users of Gemini at Galileo. I personally use Gemini as my own personal AI assistant. I don't use ChatGPT or anything else, all Gemini. And so, yeah, it's really awesome to be at Google to host this meetup. And that's it. Thanks so much for coming. We're going to do more of these. And yeah, this was definitely a very fun event because we started with 20, 30 people like a year and a half ago. And this meetup, I think, had almost 1,500 RSVPs. And we tried our best to get people from different industries and different groups here. So hopefully this is a good group. And the rest of the time, just want you guys just to meet each other and learn from each other. And yeah, that's it for today. So thanks so much for coming.